So this is on the C4 and CAM. I think every one of you did the other assignment that was due on Saturday, so that was good. And then this one will be due Saturday again. And then the lab homework assignment, quiz, whatever you want to call it, that opens up on Friday. So I will keep reminding you as we meet this week. And then I heard a few mentions about a storm coming, and yeah, there is a storm coming, and it's every time they mention it, it seems like it's getting bigger. So we'll see. It sounds like Tuesday into Wednesday, I think, right now.
Tuesday night,
Yeah.
freezing rain and the snow Monday morning.
Okay. Yeah, that freezing rain is not bitter cold, but the freezing rain is going to be an issue. So we'll see. Check your texts first thing in the morning. I think they try to make a call somewhere between 4 a.m. and 6 a.m. And then the text usually comes no later than 6 a.m. typically if Northern's closed. So I'm guessing K through 12 will be closed, but we'll see. We'll see. Okay, so we are getting into leaves. We've done roots, we've done stem, and now we're into the leaf area. So I don't know if you've seen video of some of these giant lily pads where like little kids are sitting on them. So the undercarriage, the architecture underneath the leaf can be very robust. I've seen birds also like stepping from leaf to leaf and not sinking. So they're a remarkable aquatic leaf. And the sometimes they will be a little bit of a nuisance because they'll get so abundant in the rivers that they will essentially block out the sunlight for plants that live, submerged plants that are all the way under. So that can be a problem. But we don't have leaves like that up here. This is more tropical. Look at that one. Giant rhubarb, and also nicknamed dinosaur food. So you can see the guy's head there for the relative size. I don't know that I want that in my yard. Here's someone's landscaping with it. Yes.
You know that right right down the road,
Yeah.
right by the like power station or whatever, they have like that one trail
Yeah.
and then it's got like all the graffiti on it. Do you know what the giant plants
Yeah.
that are there?
Yeah. Does anyone know the name of that? It's all over there. It's invasive. It's not good.
But then they like signs like it's a restoration project.
Yes, they are trying
Like,
to.
so are they planting it or are they trying to
No, they're trying to get rid of it. It's just massive. It's on both sides of the road, right
Yeah.
street there. It's on both sides of the road. It's very invasive. I'm blanking on it at the moment. Dr. Robertus knows about it. He knows the right name, but I'm blanking at the moment. But yeah, they're trying to get rid of that it just encroaches.
Mhm.
This might be in the same family. It's not the same species. This is more tropical, but I did see a plant like this close to campus years ago, but when last summer it looked like they chopped it down. It wasn't quite this dramatic, but it was definitely noticeable in their front yard. But I think they got rid of it. So leaves, when you look at the entire plant body, leaves are the most diverse in morphology. You have lots of options when it comes to leaf design, and you can use that as a way to identify. I would like you to know what it means to be opposite and alternate leaf. So you see alternate, they alternate left, right up the stem of the plant. Opposite means they're attached at the same spot on either side of the stem. Whorled, I'd like you to know that one too. That's where you have three or more attached at the same point in the stem. You don't need to know decussate, spiral or helical is a pretty good one to know. But if you get into identifying plants, the terminology will be important. But you may hear me using alternate, opposite, and whorled probably more than any of the others. So we have this idea, whoops, that leaves can be compound, or simple versus compound. And so um, here you're seeing some options for compound on the top. So this is palmate compound. So that's referring to the palm of your hand where you have kind of all the leaves attaching in the kind of like central to your palm. They're coming out from that as you look at it, especially, looking down on it. Palmate, compound pinnate. Pinnate, usually when you hear that word, the leaves are right across, or leaflets are right across from each other. So when you look at a compound versus a simple, the way to figure that out, this is a better idea here. With a compound leaf, what they mean by that is that you don't have any axillary buds in these regions here. Okay. You only see an axillary bud at the base there. That's your giveaway. That's your dead giveaway that what you're looking at here is a compound leaf because you don't see any axillary buds in these regions. So then that means that each of those are called leaflets, not leaves. So this leaf that you see on the right, it's a compound leaf composed of leaflets. Does that make sense? Okay. Then the simple leaf, you see this whole thing. Yep, that's a leaf because you have your axillary bud right there. All right. So that's the way if I see leaves, and leaves, like I said, there's all kinds of different designs. So I'm always looking for the axillary bud to see if it's truly a simple leaf or if it's a compound leaf composed of many leaflets. So look for the axillary bud. Here's another. Okay, so that can be tricky if you don't know this idea. It can be hard to tell sometimes. So let me go back. Okay. Shapes of the leaves can vary tremendously. I don't really, for this class, you don't need to know the terminology. I'm not asking for that. I'm more interested that you understand it can vary tremendously and that you look at size, you look at shape, you look at vein pattern, all of that. Yes.
Going back to the compound leaf,
Mm-hmm.
if you like chop it in half, will it like, because there's no auxiliary bud on
Mhm.
that side, so it can't like regrow that way. So will it grow a whole new compound leaf or will it
Mhm.
just stay the way it is?
Yeah. So like if you um take a cutting, you mean? Like here? Is that
Like
what you mean?
on the actual leaf itself. If
Here?
you chop, yeah. If you chop that or like past the first leaflet, if you chop that off, will the plant grow like a whole new compound leaf there?
Yeah.
To, like,
So the oxen will still be coming down here,
Mhm.
flowing down. So I would suspect that if you cut here and take off, well, you wouldn't have those because you cut, and probably take these off and then plant it in water, that you'd get adventitious roots there. And if you let it grow long enough, you'd start getting more biomass. And it should give you that leaf design. Here's another idea here where you can see as you are hunting, there's lots of axillary buds here. So all of these are leaves that it looks like they're alternate going up the stem. Okay. So even though it kind of looks like this one, this, all of these are leaves. This is a bunch of leaflets. That makes sense? Close up. So sometimes the axillary buds are quite diminutive, quite small. So look for them. Another weird thing about leaf morphology is it can change depending on the age of the plant. So here you're looking at the same plant, different ages. So on the smaller image that you see, that's the juvenile phase of the plant. You can see its leaf design is very, very different compared to this bigger image here on the right. That's the adult. So once this plant goes through and shifts from juvenile to adult, it's kind of like our puberty into adult or pre-puberty into adult. You'll see a shift in the leaves. So that is tricky. So I sometimes have had students bring me a very young seedling with some very, it's really young plant. And sometimes you don't always know exactly what you're looking at until it matures a little bit. Although now with Google Lens, you can usually take a picture of it and they usually have a source that will tell you what it might be. Here's some more ideas. Juvenile on the left, adult. We go from more needle-like to scale-like and juniperous. And then you can see the morphology on the right there with the English ivy. You get some very different overall shapes. So keep that in mind as you're looking in growing plants. You might see a shift. When you go to identify, you do look at the perimeter of the leaf to see what it looks like. Again, I'm not going to ask you to memorize these names. However, the venation pattern, that concept I want you to know. So parallel versus netted, and you can have different kinds of netting, pinnately, net veined, palm veined, net veined, palmately. That's not so much. I want you to know parallel versus netted. Those are the two big distinctions. You either have veins that run parallel to each other or netted like a fishing net when you look at the vein pattern. So that you'll need to know because that's a good way to identify if you're looking at a monocot versus a dicot. So up close, netted venation on the left, you can see if, especially as you include in your visual, as you're looking at it, all the little minor veins, not just the major ones, but the minor ones, you can see that it's very net-like. And then the parallel venation on the right. So parallel venation can be like that, where they kind of swoop away from the midrib like that, the mid vein, but they're still all parallel to each other on each side of the main vein. And then here you see it's just parallel all the way across, from top to bottom. And then netted venation, here's where there's a technique you can do to take leaves and digest away all of the cells except for the veins, the vascular bundles. And that's where you can really see the vein pattern if you do it carefully. Okay. So the veins, of course, that's the vascular tissue. We're getting into the xylem and phloem. And so we're going to start looking at that. Don't forget that when you are looking at leaves, you have the fancy name is the petiole. That's the leaf stem. We call it the petiole. And when you look at a leaf drawing, I think I've shown this one at least once, if not more. This is a very typical way to demonstrate leaf anatomy. And so the way the artist has drawn this, I know that they were thinking of a leaf that spends a good portion of its time horizontal to the ground and rather than vertical. And the reason I'm thinking that way is that the way the stomata are drawn, they're only on the bottom. And we'll get into this a little bit more, but if leaves spend their time pretty horizontal to the ground for most of their life, having your stomata on the shaded underside where it's a little bit cooler, it's more humid, that can actually slow down your water loss, your transpiration rate. So we'll talk a little bit more about that. Okay, so here, just reminding you about the anatomy. You have the epidermal layer. It's typically one cell thick, but not always. You tend to have that waxy surface covering the cuticle area. And then it's pretty typical that you'll see this design. And when you look inside, you'll have the palisade parenchyma cells and then the spongy parenchyma cells. And then, of course, you have all the veins, which are the xylem and phloem. And then don't forget with the surface area with the epidermis, you can have slightly different types. These look more like jigsaw cells, but sometimes they look more brick-like. But you can definitely see the differentiation of the stomata, the guard cells with the pore scattered out like that. Here is also, these are dumbbell-shaped guard cells. They look like dumbbells that are surrounding the pore. So this one on the right is common like in corn or maize plants. You'll have that design. We've talked a little bit about this idea that the guard cells regulate the size of the pore when you look at the stomata. And so that's really due to the idea of turgor pressure, how the water is rushing in to the guard cells. And when that water rushes in, it gets the guard cells to move away from each other with the turgor pressure building up. And so they're trying to show here all those black lines that you see. That's trying to show how it's the design of the cell wall. There's these special microfibrils that get really beefed up so that they're kind of like radial tires in a way. But with that design, when water is exerting pressure on that design, it causes this bending of the guard cells. And that's what's allowing the pore to get opened up. And then it's just the opposite. If water exits out of the guard cells, then you have the guard cells collapsing and going flaccid and they cover over the pore. And this is really tightly controlled by the plant. They can open it up 100%, close it down to 0, and anywhere in between. It just depends on water availability in the soil, temperature, humidity, all of that we have to think about. So when the water is exiting the plant, it'll primarily go through the stomata. Everywhere else is pretty well waxed and hydrophobic. So the plant is trying to only have water loss occurring in a spot that it can control it by the guard cells and whether or not those will be open or closed. So when we talked a while ago about how water moves through the plant, do you remember what we were saying about that? How water is moving primarily, especially when you think about the really tall plants, what is the method that they think is happening?
Cohesion.
Cohesion, yep, cohesion tension theory. So which one sounds the most likely there?
Okay.
Pushed up means like a positive pressure. So when you use a straw to drink your soda pop or whatever, what are you doing? A or B? B. You're sucking up through the straw, right? That's kind of what the plant's doing when you think about it. They're opening, hopefully, when the sun strikes their body, when sunrise occurs and there's enough water in the soil, they'll open their stomata right away to take in the CO2 for photosynthesis. And this is trying to show this compromise. Yes, they want CO2 to make sugars, but as soon as they open their stomata, by default, water is going to exit out of their body in the form of water vapor. So what's happening here is in the xylem where you have all that water movement. Remember, we're thinking about water and dissolved minerals and also dissolved gases. I think you should add that. the dissolved gases idea is going to come into play here a little bit. Whoops. So dissolved gases are happening as well. We said it's unidirectional flow. So it's only one direction in the xylem. They've never seen water being brought into the plant through the leaves and going down to the roots. It's always soil, water into the roots, dumped into the xylem, and then it courses through the whole plant body, gets to the veins of the leaf. And then once it gets into the air spaces of the leaf, it converts over into air or water vapor, and then it exits the leaf. So you have to imagine, especially if there's a lot of spongy mesophyll cells, remember there's a lot of air pockets in the leaf. So when the water is getting pulled up the plant through the xylem, it's liquid. And what happens is all the liquid molecules start to kind of cling to the internal leaf cells. And then from the surface of the leaf cells, they evaporate into water vapor. So that's all happening amongst all these cells. And then the water vapor will exit out through the stomata. So this idea of this constant compromise and the plant's constantly assessing how much water do I have? How much water do I have access to? And can I keep my stomata open or should I start closing down? And then the risk, of course, is if you close down for too long, then you don't have CO2 coming in. And so your photosynthesis stops. So it's always a risk and like a compromise, as they say. So in order for transpiration to happen, you got to have the stomata open. Otherwise, it's not going to happen. Because if you don't open the stomata, you won't have any tension force, which I'll explain a little bit more about. So the stomata must be open because as soon as that happens, you'll get water vapor exiting out through the leaf, and that triggers a tension gradient on the liquid water that's felt all the way from the leaf veins all the way down to the roots in the xylem. And that is a gradient that will be felt, and it allows for water to be sucked up. And so that force is generated all due to the stomata opening up, right? So that idea of water getting pushed up the plant, they've debunked that. It can happen if you're a very tiny plant, short plant, you can get that under the right environmental conditions. You'll get a little bit of positive pressure building up in the xylem, but that's only under special circumstances. And especially if you think about giant redwoods or something like that, the cohesion tension theory is what is explaining it. You have all those water molecules cohering to each other, so they form this nice solid column of water through the whole xylem. You have the tension idea where the tension is generated up in the leaf as soon as the stomata open up. So this is also showing this idea where you have to imagine the liquid water coming out of the xylem and kind of clinging to the surface of all these cells. And then those liquid water molecules evaporate into the air spaces there and then exit out of the leaf. And as that's happening, you get a tension force building up on the liquid water. And that's felt all the way down to the roots. So if you think about it, here they're trying to show down at the roots on the bottom of this picture, water coming from the soil being brought up into the roots. Primarily the root hairs are responsible for that. And then they're showing once it gets dumped into the xylem, it just courses up through the connected xylem cells. They're trying to show that water is just one big column of water. Okay, it's all just water molecules and the dissolved minerals and dissolved gases. And so you have cohesion, water molecules like to bond to each other. You have very small diameter of the xylem, so that allows for that capillary action to occur as well because of adhesion. And then they're trying to show finally, once it gets to the leaf, that you have the liquid coming out of the vein, clinging to the cells inside the leaf, evaporating, and then exiting out of the cell, of the leaf. Here's another image. So really it's the evaporation of water vapor that's really triggering this tension force that originates in the leaf. Now they're showing one additional idea here, which is cavitation. So we said that the xylem has water, dissolved minerals, and dissolved gases. If you've ever done any experiments like in physics class or something where they have gases dissolved in liquid and then you put a tension force on that, it pops the gases out of solution. Okay. And it's kind of like getting an embolism in your blood vessel system. It's kind of like that idea. Is it good to have embolisms in your blood vessel system? No, that could kill you. Luckily for plants, it doesn't kill them, but it's not good for them either. It's not quite as serious. But what happens is if the tension force is pretty strong, and that usually occurs under drought conditions where the plant is getting less and less water getting brought up, but you still have a really strong tension force. Sometimes you can get the air or gases in general, the gases popping out of solution due to that tension. And that it's like a little embolism for the plant. And they're trying to show that if that happens, that particular trachea or vessel is useless now. Water can't get through that air pocket. And so they're showing that the water is rerouting. Remember, xylem and phloem, and there's a bunch of them clustered together. And that's a really good design for, especially if this happens, because then you can get rerouting of the liquid water around any air bubbles that are occurring. The fancy name is cavitation. I would like you to know that. So cavitation, equate that with an embolism, like in our blood vessels, except it usually doesn't kill the plant. And so as you get into more droughty periods, like late summer, typically you'll get more and more tracheas, and especially the vessels, mostly vessels, they'll get these cavitations going on. And sometimes it's repairable at night. So what do you think happens when the stomata close at night? What happens to that tension force? It's relieved. Okay. Everything kind of relaxes. And so as that happens, you can get those air bubbles redissolved back into the water. And so it's not necessarily a done deal. It really does depend on how good the plant is at getting that happening overnight. But vessels are definitely the trickier situation. So why is this so fussy? Vessels, if they have cavitation, it's more challenging to get those gases back into solution because the vessels have a wider diameter compared to tracheids. So a narrow diameter, it's easier to get that gas back into solution. A big area like that in a vessel, that's tougher. It's a bigger bubble. It's just tougher to get it back into solution. Does that make sense? So that's one reason why plants, angiosperms, say, I'm going to make vessels in the spring when there's all that great water availability in the soil. You've had plenty of spring rain, the snow melt, all of that. The soil is great, nice and moist, lots of water in there. So they'll put vessels down, vessels, vessels, vessels. But then as they start sensing drier soil, they'll switch to tracheids. And it's mainly because they're trying to prevent cavitation from occurring too much. Questions on transpiration? We go into this in more detail in Plant Phys. For those of you who have Plant Phys, you know way more than this. But for this class, we'll keep it at that level. One thing to think about, going back to this picture of a leaf in cross section, you see this boundary layer that they are talking about on both sides of the leaf. Okay. So any physical object has a boundary layer to the air around it. You have a boundary layer, your skin to the air. So do plants. Plants have a boundary layer too. And for them, what it is, well, for all of us, what it is it's a layer of relatively still air molecules. Okay, so the layer of air molecules right on the surface of your skin is pretty still, not much happening there. And you can think about it like if I make you run, or like, have you been watching the Olympics? Wow, those athletes are amazing. And so, you know, you work up a sweat doing your downhill slalom, and then I stuff you into a room. You get stuffed into it one time where still air, 80% humidity. And then the next time you run your giant slalom race, and I stuff you in another room with a wind of 15 miles an hour coursing across your body. Which condition would the sweat leave your body more quickly? The wind. Okay, so think of that idea with the boundary layer. What's really happening is as you're getting that wind across your body, you're thinning out this still air. This boundary layer gets really thin because now all those still air molecules, because of the wind, they're getting stirred up and getting more kinetic. And so your boundary layer thins out. That's actually going to speed up your sweating. You're going to feel cooler much more quickly. And that's the same with the plants. The water vapor exiting the leaf, it'll be a quicker transpiration rate. So think about that. Windy days, modestly windy days, you're going to have transpiration rates faster than on still days. Low humidity days, you'll be able to sweat a little bit better and feel cooler than if, you know, it's 90% humidity, then you just feel so sweaty and yucky. So if you use that analogy, I think it's a great way to think about what's happening also with the plant. You know, they have a boundary layer too, and it can impact how quickly their transpiration is going on, how quickly that water is going to exit their body through the leaf stomata. So this one, they're showing both what's going on in the xylem, and then they're also showing photosynthesis occurring. And so it's important to realize that with water absorption, it's all unidirectional through the xylem. With the phloem, however, once they make their sugars, it can go every which way. So sugar in the phloem, in the sieve tube elements, you can have some of the phloem delivering sugar out laterally. Some of it goes up, some of it goes down to the roots. And so you can get sugar delivered any direction through the plant body. It just depends on what part of the plant body needs it the most. They can tell, and they're able to funnel the necessary nutrients, especially if, you know, if it's the time of the year when that plant's making flowers or fruit, for example. You're going to get a lot of sugar delivered that way, less sugar delivered to some of the leaves, for example. And so this sugar production, when you get it dumped into the phloem, they're trying to show it can kind of go pretty much any direction for the plant. So it's really different. Even though the xylem and the phloem are right next to each other, you have some definite rules to follow that are different between the xylem and the phloem. Okay, so this is a cross section of a leaf. And this is kind of drawn, or kind of looks like the drawing, where you have all of this area here. Those are palisade parenchyma cells, and then you can see spongy parenchyma cells. can see a big central vein. That's vascular tissue. So when you look at the leaf slides in lab, kind of train your eye to this, be able to identify the palisade versus the spongy, be able to zoom in on veins, vascular tissue. Here's a nice comparison. This is the same plant. So this is a maple tree. And you have very different looks when you look inside. And even the thickness of the leaf, you can see overall, there's a difference. So what's happening here is the leaf up top, this is your sun leaf. These are the leaves that are mostly in the sun all the time on that tree. So you're thinking about the leaves on the very upper of the crown of the maple tree. The lower image, those are shade leaves. So those are the leaves that spend most of their time. They must be lower down in the branches of the canopy of the tree, and they're shaded quite a bit. And so you can see here that in the sun, they've beefed up their palisade cells. It's overall thicker. They don't show it. These two don't show it, but sun leaves are thicker and less surface area. So they're usually a little bit smaller in surface area compared to sun leaves, and they're thicker. Shade leaves, on the other hand, they are thinner, but they spread out to try to catch little chinks of light in that area. So you can see that the shade leaf is thinner. Um, here's a vein. Here's a vein. You can see. So one plant, it's pretty amazing how they can alter their morphology of their leaves. It's the same exact plant, but on different parts of the tree, you can see different design of the leaves. If for some reason, let's say the shade leaves, let's say some branches above fell off or got cut off, and all of a sudden now that section of the plant is exposed to sun, the new growth will shift into sun leaves. So they're very adaptable. It's really driven by the impact of the sun and how long those leaves get exposure to sun. So they're able to adapt on the fly with new leaf tissue. So when the person made this image, they took the leaf and cut it in cross section. And so now you're seeing veins that are essentially coming out at you. Does that make sense? The two veins are coming out at you. So is that netted or parallel? Yeah, that's parallel. So this is parallel venation that you're seeing. And when you think about that, in that image, let's go back, let's show another. Let's look at this image. So now this is tricky. This is a vein coming right out at you. And believe it or not, this is a vein that got cut. So it's like the first one I circled, this one. It's like the vein is coming out at you, and when they took a cut, they cut it this way. Now, with this other one, this vein happened to be going this way. So when they took the cut, it went down like a longitudinal side of the vein. Does that make sense? So you're seeing one vein coming this way, one vein going that way. What is that? Netted or parallel? Yeah, it's hinting that it's netted. So depending on who makes the cut, I mean, I'm sure they kind of did this by accident, but it's a great demonstration of when you look at a leaf under the microscope, you can actually get a lot of information about that plant. And vein pattern being a good one. Here's another one with veins, 3 veins being shown, and they're all coming out at you. So this is parallel. So you would need to look at a few preps of the same leaf just to convince yourself. So for example, going back to the maple, they're a dicot. So this prep didn't show one of the veins in cross section. So um, you'd have to look at several preps of it to verify. Okay, another thing about this to look at is when you see the pattern of palisade cells, even if they're built up like this, and then here there's not as many palisade cells, but you can see, and then the spongy mesophyll below it like that. I can tell that this is a plant whose leaves do spend the majority of time pretty horizontal to the ground. They tend to have this design of palisade on the top, spongy on the bottom, and then they tend to put most or all of their stomata on the underside, where if they're horizontal to the ground, that means the cooler underside of the leaf. Kind of makes sense to put your stomata there so that you can open your stomata even if it's really hot. You can be a little bit cooler on the underside, a little bit more humid, and so you don't risk losing water too quickly. It slows down transpiration if you stuff your stomata on the underside, the shaded, more humid portion. Okay. Now, there's plenty of leaves that spend their lives more vertical, either upright or pendulant like this one. So then what do you do with your stomata to try to minimize transpiration? And you don't really have an option here because if you think of a normal plant living its life, it has, let's say its leaves are more upright. So if that's north, that's east, right? So as the sun comes up, you have this side of the leaf getting hit with morning sun, then high noon, and then afternoon, evening sun. So it's like the same amount of sun on both sides. So it doesn't really matter where you put your stomata, you're going to have sun showing up pretty equally on both sides of the leaf. So you would do something like this. You can see here that there's stomata on both sides of the leaf. And so that's a tip off that you're probably looking at a leaf that's more vertical most of the time. The other way I can tell is that vertical leaves tend to have this pattern of palisades on the top and bottom and the spongy mesophyll kind of stuffed in the middle. You can kind of see that pattern. And the way I look at it when I'm looking at them under the microscope, I always take a cross section like this and I mentally cut it in half. And then I ask myself, do they look like mirror images pretty much to each other? And they do. You have palisade, spongy, spongy, palisade. So that's a pretty good rule of thumb that you're looking at a leaf that spends more time vertical to the ground. Same with this one. If you cut it in half mentally, you have pretty much the same on either side, symmetrical like that. So again, this plant spends most of its time vertical. This is maize. This is a maize plant. If you've ever walked through maize cornfields, they do spend most of their lives vertical like that. The other reason, so this is a monocot. We already talked about that. All the veins are coming out in parallel. Well, what am I doing here? I can't talk and write at the same time. So monocot. Monocot has parallel venation. Okay. So parallel veins, that's usually a dead giveaway that you're looking at a monocot. And then with a netted vein, that's your dicot. Okay. Netted vein pattern. So we're going to be looking at what makes, how do you figure out monocot versus dicot throughout here as we work. Okay, I need to stop. I still have more to say about all of this, but we'll come back to it. And let me open up EDUCAT so you can look at your essay results.